Today we have to discuss about polymers. These slides were prepared as accordance with the fourth semester complementary course. It's a module uh, detailing about the polymers, classification of polymers, and some polymers used in our daily life is also described. So there is no detailed description about polymers. Actually, because of the time constraint and also the data consumption is concerned, we will talk about the most of the main points even in the topic. And if you have any doubts, you can contact me in this regard. So we will start what is a polymer. As you know, everybody knows what a polymer is. Because as the first slide it shows that a bigger molecule over here, and there are several repeated units also present, and this bigger or longer or macrocyclic material is what is called polymers. Now this is what everybody knows what a polymer is. It is a large molecule or macromolecule or composed of many repeated subunits. As you know, polymers are composed of several repeated units, and the molecular weight of the material is also very high because of several number of tiny units present in it. And these tiny units from which the polymer is made is what is called monomer. So in Greek word, poly means many, mer means part. Many part is what is called polymer. So in other words, a large number of simple repeating units linked together through covalent bond are called polymers. They are also called as macromolecules. Monomer is individual small molecules from which the polymer is formed are known as monomers. The Greek word mono means single, mer means part. Many, single part is the monomer. And polymers may be divided as biological and non-biological polymers. Polymers can be divided into several categories depending on the type what we want to describe about it. Here, one way of divide polymeric materials is biological polymers and non-biological polymers. Biological polymers means the polymeric material that is present in the biological system. Non-biological polymers means that is not that is synthesized by human being or synthesized in the industry or synthesized in the laboratory. So first is the biological polymers. They are important cellular components and perform a wide array of functions necessary for the survival and growth of living organisms. For example, carbohydrates, lipids, proteins, nucleic acids, etc. So these are all very much required for the proper functioning of the human being, the cell of the human beings. And also non-biological polymers are synthetic polymers. They make our life more easy and convenient. As you know, after the discovery of polymeric materials, our life was moves very smoothly, and because of the use of polymeric materials in our daily life. For example, clothes, utensils, shelter, communication, and so on. The drawback of synthetic polymers, as you know, for example, like polyethylene, polypropylene, etc., are not biodegradable. This is the major and serious drawback of synthetic polymeric materials, and they pose serious threat to the environment as a persistent pollutant. So that is the major issue of the polymeric material. Otherwise, polymeric materials are actually the wonder material. Next is polymerization. Polymerization means the process of synthesizing the polymers is what is called polymerization. The process by which monomer molecules are linked to form a bigger polymer molecule is called polymerization. As you know, ethylene, the molecular weight of ethylene is 28. Just 2 carbons and 4 hydrogens are there. 2 carbons are linked by a pi bond. In the presence of trace amount of oxygen, heat and pressure, we are getting the polyethylene. So you know the atoms present in polyethylene is carbon and hydrogens only. So actually 4 hydrogens are here, 4 hydrogens are also here in the repeated unit, and 2 hydrogen carbons are here and 2 carbons are here in the repeated unit. And only the pi bond is broken over here, or it has converted into form single monocovalent bond. And this is the repeated unit, and several such repeated units will form the polymer, and the molecular weight of the polymeric material will become several lakhs. So it is schematically shown here. Polyethylene is shown here. The carbon-carbon double bond is broken, and then it forms covalent carbon-carbon backbone and hydrogens on the carbon atoms. Now let's see some examples. Vinyl chloride polymerizes to yield polyvinyl chloride. As you know, everybody knows PVC. It is a well-known polymer. So vinyl chloride is shown, CH2 double bond CHCl. It polymerizes in the presence of peroxide and heat, and then we get polyvinyl chloride, CH2 CHCl n times. Here also the carbon-carbon double bond is converted to the covalent single bond. Next example is propylene polymerizes to yield polypropylene. CH2 double bond CH3 is propylene. Polymerizes in the presence of a Ziegler-Natta catalyst, triethyl aluminum and titanium tetrachloride, and heat it. Then we get polypropylene, CH2 CH3 n times. There are several types of polymers are present. For example, nylon polymer. So this is formed nylon, or it is polyamide. An amide linkage will be there in the polymer, and this polymer is formed by polycondensation method. As you know, condensation method means two reactive molecules will react together, and by the elimination of a small molecules like water, carbon dioxide, ammonia, etc., it forms another material. And here hexamethylene diamine NH2 CH2 6 times NH2 reacts with adipic acid COH, CH2 4 times COH, and then we get nylon 6,6. Here a molecule of a number of molecule of water is eliminated. So here OH and then one hydrogen from the NH is eliminated as the water, and then it forms NHC double bond O. So this group is what is called the amide group. So n number of these groups will be present in this molecule, in this material and this polymer, and we call it as a polyamide. Nylon 6,6, the name came from 6 carbon atoms are here, and on this also 6 carbon atoms are here. So this is nylon 6,6. So it depends on the name comes from how many carbon atoms are there in the reactive molecule. Next, we are giving a detailed description about the classification of the polymeric material. So first classification is based on origin, because polymeric materials form naturally, and we have to call that polymers are the natural polymers, and then synthetic polymers also there. And first is the based on origin, natural polymers. The polymers which are found in the nature, in plants and animals, are called natural polymers. For example, starch, it is a monomer, unit is alpha glucose. Cellulose is beta glucose. Proteins, alpha amino acids, and rubber, monomer, unit is isoprene. It is polyisoprene. So if you want, you can search it in the Google. What is the difference between starch and cellulose? Only difference is alpha glucose units are combined together, beta glucose units are combined together. If you are interested, you can just look into the Google. And you can also look into what is the protein. And next is the synthetic polymers. Synthetic polymers is man-made polymers in the lab or industry. As you know, polyethylene, PVC, polyethylene terephthalate, PET, etc. are examples of polystyrene, etc. are example for synthetic polymers. Next classification is based on the structure. Linear polymers. because polymers, once when it is formed, there should be different structures are possible. One is a linear structure. For example, we had shown here, it is a linear structure. And then in certain cases, there will be certain branching will also be possible. So here we are classified the polymers depending on the structure. First one is the linear polymer. These are polymers in which monomeric units are linked to form linear chains. These linear polymers are well packed and therefore have high densities, high tensile strength, and high melting points. So as you know, there will be several such linear polymeric chains will be present in the polymer, and all these are stacked over one another, and then so it will be well packed. Then for how density will be very high because there is no voids between the polymeric chains, and because of it has high tensile strength and high melting point. High tensile strength you might have heard about when we talk about polymeric materials, the word tensile strength repeats itself in several times. Tensile strength is nothing but it is the measure of the force that required to pull something till it breaks. So if you apply certain force to pull something till it breaks, how much force we have applied? It's a measure of the force, how much you applied till it breaks. So in other ways, we can define tensile strength as it is the ability of the material to resist the force that pulls it apart. I mean, when a force is applied on a material to pull it apart, but how much the material is resisting that force. That is what is called the tensile strength. The examples are high density polythene, PVC, nylon, etc. A linear polymer, monomer A, monomer is shown, and it forms the polymer, so it forms a linear polymer, it is in a one direction. And next is the branched chain polymer. So here the schematic is shown here. A polymeric chain is shown, and then there will be different branches are possible. So this is the branched chain polymer. These are polymers in which monomers are joined to form long chains with branches of different lengths. These branched chain polymers irregularly packed, and therefore they have low tensile strength and low melting points than linear polymers. So here actually what happens is, if this is a polymeric chain and there will be short branches are there, if there is another polymeric chain is there, if there is another branch suppose, and there will be, because of this branching, there may be some voids will be created, so the packing may not be that close. So the possibility for low tensile strength if there is branching. So it is shown A as the monomer unit, and then these dots are representing the functionality of the monomer unit. So it has the possibility for polymerize to this direction and this direction and this direction. Okay, so here it is polymerizing and short branches are appeared on the main chain. For example, low density polythene, glycogens, etc. Next is the cross-linked polymer. So here we are discussing the structure classification. So here the schematic is shown here. There are, you can see the polymeric chains, and these polymeric chains are connected through other polymeric chains. So there will be certain bridges are introduced between the linear polymeric chains, and this is what is called the cross-linking of the polymers. These are polymers in which monomer units are cross-linked together to form a three-dimensional network. So it has a three-dimensional network because of the presence of this cross-linking. These polymers are hard, rigid, and brittle because of the network structures. So whenever the cross-linking is there, normally the polymeric material will be more brittle and it will be more rigid and more hard. For example, melamine formaldehyde resin, bakelite, etc. So you just look into Google, you will know what is a melamine formaldehyde, and you look at what is a bakelite, then you will get what it is. Next classification is based on the mode of preparation, how we are preparing the polymeric material. There are two major methods generally used for preparing the polymers are addition polymerization and condensation polymerization. Addition means the monomer units are added together to form the bigger polymer. It is called addition polymers. As we had seen in ethylene, the monomer units are just added together. But in case of condensation polymerization, there should be certain reaction will take place. Two monomer units will react together and a small molecule will get eliminated, and these two monomer units are combined together to form. In each step reaction will take place. So that is what the condensation polymerization. So first let us discuss the addition polymerization. Polymerization is possible with molecules of the same or of different monomeric units. It is not necessary that it will react with only same monomer units. Possibility for the different monomer units are react to each other. When molecules just add on to form the polymer, the process is called addition polymerization. The monomer species in this case retain its structural identity when it gets converted into a polymer. So we will discuss it. The molecular weight of the polymer is roughly equal to that of the monomer molecules which combine to form the polymer. For example, we have taken ethylene, CH2 double bond CH2. As we have already discussed, the number of carbon atoms and number of hydrogen atoms in the monomer unit and the polymeric unit is also same. Okay, it is just added to each other. The molecular weight is not changing here. The reactant molecule is ethylene. It is just reacted or added to each other, and then continuous reaction is taking place. We get polyethylene. The double bond is a great place for the reaction to occur. Here, double bond, pi bond is broken, and it forms a single covalent bond. So this is the reactive center where the reaction starts. The electrons available here to make new bonds. As you know, pi bond, the electron density of the pi bond is higher as compared to the sigma bond. The monomers used here are unsaturated compounds such as alkenes, alkadines, and their derivatives. You may be knowing about alkadines. For example, 1,3-butadiene, two double bonds are there. That is what is called alkadine. This mode of polymerization can take place through formation of either radical or ionic species such as carbanion and carbocations. So this is all about the mechanism how the polymerization is taking place. Either free radical polymerization will take place. As you know, free radical polymerization and there are different steps in polymerization. As you know, one is the initiation reaction, that is the monomer units are initiated for the reaction by some other reacting species, and the next step is the propagation reaction. The initiated or active monomer units are propagating to form the polymer, and then the final step is the termination reaction. The growing polymer chain is terminated to polymeric material. And there are different mechanisms are there. Carbocation intermediates will form, and then further reaction will carry out, and then anions will form, and then the reaction will carry forward. The polymerization proceeds by a chain reaction involving the successive addition of the monomer molecules to the growing chain very rapidly. So reaction, once it starts, it goes very fast. Very rapid reaction will take place. This kind of polymerization is known as chain growth polymerization, or chain reaction polymerization, or chain polymerization. So addition polymerization, chain growth, the chain is growing, chain growth polymerization, or chain reaction polymerization. It is taking place along the chain, or chain polymerization. The resulting addition polymer is called a chain growth polymer or chain reaction polymer or chain polymer. Examples: polypropylene, PVC, polystyrene, etc. Next is the condensation polymerization or step growth polymerization. As we have already discussed about condensation polymerization a little bit, it is otherwise called as step growth polymerization or step polymerization because reactant molecules or the reactive functional groups will be present with the monomer units, and the reaction is taking place in each step. The reaction is taking place step by step. So here this reaction is not as fast as addition polymerization reaction. So this goes little slowly as compared to the previous one. So in this polymerization reaction, molecules do not just add on, but also undergo some reaction in forming the polymer. It is a process in which two or more monomer entities condense with the elimination of small molecules like water, hydrochloric acid, HCl, NH3, CO2, etc. to form a polymer. The resulting polymer is called a condensation polymer. The condensation reaction takes place between two reactive functional groups. Condensation polymerization generally involves building up of the polymer chain in a stepwise manner. This is what we are discussing, stepwise manner. Each step being an independent reaction. And the process is therefore called as step growth polymerization or step polymerization or step reaction polymerization, whatever it may be. The molecular weight of the polymer formed will be lesser by the weight of the simple molecule eliminated during the polymerization process. This point means that in addition polymerization, simply the monomer units are added together. So the molecular weight of the monomer unit is simply added together. But in this case, the monomer units are not simply added together, but a small molecules will get eliminated during the reaction. So the polymer molecular weight is less than how many small molecules are getting eliminated during this reaction. Okay, so this is the molecular weight of condensation polymer is the deciding factor. The example, polyethylene terephthalate, PET, PET. We are very commonly using PET bottles, or sometimes it is called PET, and nylon 66, Glyptal, etc. The brand name of PET in UK is Terlin, and in USA it is Dacron. So different names are there, Terlin, Dacron, etc. All are the same material. And how this material is reacting. So when we take ethylene glycol, CH2OH, reacting with the terephthalic acid, so a number of water molecules are getting eliminated, and it forms a polyester, aromatic ester. Here you can see that is C double bond O, CH2. So this is an ester group. So polyethylene terephthalate. It is an ester of terephthalic acid and ethylene glycol. So this is polyethylene terephthalate, CH2, polyethylene terephthalate. And this is Glyptal, is formed from ethylene glycol, CH2, OH, ethylene glycol reacting with phthalic acid. Instead of terephthalic acid, this is phthalic acid we are taken, and then it forms another ester. It is Glyptal. Based on molecular force. So actually we have to think it in terms why polymeric materials are not degraded. The answer is here. Based on the molecular forces, we can classify the polymeric material because of that accumulated force. As you know, it is a gigantic material, gigantic sized materials, and so actually the force acting here is van der Waals force and also hydrogen bonding, etc. These are normally the weak forces, but as a polymeric material is concerned, this force is accumulated all over the material, and so this is an accumulated force, and this is very strong as an accumulated force. The mechanical properties of the polymers like tensile strength, elasticity, toughness, etc. Toughness means it is actually the ability of a material to resist both the fracture and deformation. It will resist the fracture if we call a polymeric material is tough or toughness. We have to keep it in our mind that it is resisting to the fracture of the material and also the deformation of the material. Mechanical properties of the polymers are governed by the intermolecular forces present in them. The intermolecular forces present in polymers are van der Waals forces and hydrogen bonding. So these are comparatively weaker forces, but cumulative, when it cumulated on polymeric chains, polymeric material, this is much stronger forces, will act as stronger forces. Although these are weak forces, but in macromolecules, these forces have a cumulative effect all along the chain of the polymers. Polymers are thus classified into 4 categories on the basis of magnitude of these intermolecular forces in them. First one is elastomer. Elastomer means it shows the elasticity. You can deform it. When you remove it, it will come back to the original size. In these polymers, the chains are held together by weakest intermolecular forces, which permit the polymers to be stretched. Softness, stretchability, and toughness are their characteristic properties. So note down, softness, stretchability, and toughness are their characteristic properties. A few crosslinks between the chains holds the molecules together without allowing them to slip past each other on stretching and help them regain its original position when the force is released. So this point means that when you stretch the material, if there are certain crosslinks are given in between the polymeric chains, when you stretch it, that time the polymeric chains may not slip past to each other. So cross-linking will hold the material not to deform. Then when you release the elongation, it will come back to the original level. For example, like vulcanization process. Vulcanization, the process by which a network of crosslinks is introduced into an elastomer with a view to improve its properties is called vulcanization. As you know, sulfur is normally used for as the vulcanizing agent. Some other material is also used, but here we have to focus on the sulfur. When we use sulfur as a vulcanizing agent, for example, like in vulcanized rubber, its properties will totally different. Or to improve the property of the rubber materials, normally we do the vulcanization. Vulcanization means the cross-linking is given between the polymeric chains using sulfur. So here it is shown, natural rubber is shown here, polyisoprenes is shown here, two chains of polyisoprenes are shown here. And then when you heat it with sulfur, the sulfur linkage was introduced between the two polyisoprene chains. So there will be cross-linking of sulfur. So this is the cross-link is shown. So the property of the sulfur will be different. It will be more elastic, and its property will be more superior property it will exhibit. The natural rubber can be vulcanized by heating with small quantities of sulfur at 110 to 140 degrees centigrade. Other examples means buanized rubber, synthetic rubber, bunion rubber, neoprene, all these are synthetic rubbers. These also can be vulcanized in this manner for getting superior properties. Next is fibers. As you know, you heard about the word fiber. It is the very long filament-like material, or its length to diameter ratio is very high because the length is more as compared to the diameter. So because of this, these materials are more closely packed, more strong, and can be used for more tough applications. If drawn into long filaments like materials, whose length is at least 100 times its diameter, polymers are said to have been converted into fibers. Mostly polyethylene, polypropylene, etc. can be converted into um, its fibers for different applications. These polymers possess high tensile strength. Fibers have high tensile strength as compared to the polymer as it is. This is due to the strong internuclear forces like hydrogen bonding which operates, and also these forces lead to close packing of the chains. Close packing of the chains is important and thus give crystalline nature. Because of that, these polymers show sharp melting point. They are tough, stiff, and abrasion resistant. Abrasion resistant means it is resistant to wearing and tearing. Stiff, tough, and abrasion resistant material. They retain their properties over a wide range of temperatures. So they can withstand a wide range of temperatures also. So when you make a polymeric material in its fiber form, it will show the superior property than the material as it is. For examples, nylon 66 and poly PET fibers, etc. PET fibers are PP fibers are there. PE fibers are also there. It is just showing the natural fiber, cotton, natural fiber. This is what to say, chakunulu. Okay, so synthetic fiber, nylon fiber, just to show you. Next is thermoplastics. Thermoplastic, as you know, you might have studied about thermoplastics and thermosetting plastics. Thermoplastics is the material which can be heated and then you can melt it and then cool it. You can make it into different shapes. You heat it, again you heat it and then melt it, pour into different molds to make it different shapes, and then after cooling you will get to that particular shape. So this process, heating and cooling, can be repeated several times without changing the property of the material. So you can make it into any shape, and this type of materials are what is called thermoplastic materials. These are polymers in which the intermolecular forces of attraction are midway between those of elastomers and fibers. So intermolecular forces are midway between elastomers and fibers in thermoplastics. So due to that, some polymers often on heating and can be converted into any shape that they can retain on cooling. This is what we are just speaking about. The process of heating, reshaping, and retaining the same on cooling can be repeated several times. Important. The process of heating, reshaping, and retaining the same on cooling can be repeated several times without affecting their properties. Yes, without affecting their properties. In thermoplastic polymers, there exists no cross-linking between the chains. If it is cross-linked when heating, then it will be thermosetting plastics. It is set. For example, are polyethylene, PVC, Teflon, etc. Thermosetting plastics. This is nothing but when you heat it, cross-links will form. It is set, completely set. So there is no, you cannot reheat it and remold it. So there is no repetition. Only heat it, mold it, finish. When heated in a mold, they undergo permanent change and highly cross-linked to form hard, infusible and insoluble product. Cross-linked to form hard, infusible and insoluble product. There should be permanent change. Nothing can do afterwards. They can thus be heat treated only once, cannot be remelted and remolded. The common examples are bakelite, PF poly formaldehyde, phenol formaldehyde resin, urea formaldehyde resin, UF resin, melamine formaldehyde resin, MF resin, etc. So these are the classification of polymeric materials, and hopefully next class we will discuss the other points.